Hello. So, rigged this up to try to teach this on the board so that I can write them out for you. So we're going to do the ideal gas law today. So you guys should have done Boyle's law, Charles' law, and Gay-Lussac's law last class. Those three were pretty simple relationships. You were just using basic algebra to solve for one of the missing variables. So you know that like there's P times V equals P times V, and you're balanced on either side. So you're basically comparing what you started with to what you're ending with. The ideal gas law is used for things when you're not necessarily making a comparison between two things. You just have a chunk of information and you're trying to determine one of these five variables. Um, so for these, there's a couple of rules that go with these. P is going to be pressure, V is volume. You're going to set that equal to N. N is the number of moles. R is a constant, and which value you use for R will depend on which values you're using, which units you're using for P. We'll talk about that in a second. So R is a constant that will be given, and then T is temperature. It has to be in Kelvin. Okay, so when you're looking at these, pressure is either going to be in atmospheres or kilopascal. Volume will be in liters. N will be in moles. R, we'll talk about that in a minute. And T has to be in Kelvin. All right. So with this here, we have this R. You can see that R is equal to 0.08206. And it's liters times atmospheres divided by moles times Kelvin. On your assignment, on the first page, I don't know if you can actually see this or not, you'll notice that it gives you two different values for R. Okay, so you're going to use this value for R, which is going to be 0.0825 whenever your pressure is measured in atmospheres. And the reason for that is that this is what R is calculated to be at standard temperature and pressure using atmospheres. If your pressure is measured in kilopascal, you're going to use 8.31 for your value for R. Okay, so these two numbers, this is on the assignment on Canvas. So it's the first page of that assignment whenever you look on there. So R will be this if it's measured in atmospheres, and this if it's measured in kilopascal. So we're just going to have to pay attention to that as we work and make sure that you're getting the right R constant value in there, because if you don't, it'll mess everything up. So this is just one example. I'm going to go through 4 examples for you so that you hopefully can understand how to do the assignment. So in this example, you have hydrogen gas has a volume of 8.56 liters at 0 degrees Celsius and 1.5 atmospheres. Calculate the moles of hydrogen that are present. Okay, so in this example, they went ahead and reworked this formula so that you're just solving for N right off the bat. You can just kind of plug and chug. I usually keep it in this format and then just solve from a missing variable. Either way is fine. If you do it this way, it might be more useful in like upper level chemistry classes if you're taking that in college, so that you are just familiar with rearranging and deriving equations. But for us, for this class, using PV equals nRT is just fine. So here they went ahead and reworked this to solve for N. All they did was substitute in the values. Okay, so pressure is 1.5 atmospheres, which came from the equation or from the question. 8.56 liters, it was already in liters, so you didn't have to change anything there. R is going to be the R value. Okay, so R is either going to be this or the 8.31, depending on what your units for pressure are. So since my units for pressure in this question were in atmospheres, that means I'm going to use this R value times my temperature in Kelvin. Okay, so if you don't remember, changing Celsius to Kelvin just means that you have to add 273. So that's pretty easy conversion there. So let's go ahead and move on to one and kind of work it out as we go. So these are the same ones I'm doing in class with the kids in class. So just fair warning, this video might be a little bit longer than the others just because I'm going to be working through these with you. So on this first question, calculate the mass of krypton needed to fill a balloon to a volume of 11.0 liters at a pressure of 104.8 kilopascal and a temperature of 32 degrees Celsius. Okay, so the first thing you want to do is pull out all of your knowns. Okay, so let me make sure that my marker's all set up here. All right, so what do we know? Okay, so we know that the volume is going to equal 11.0 liters. We have pressure at 104.8 kilopascal. Okay. We know the temperature is going to be 32 degrees Celsius. So we're going to have 32 plus 273. Okay, so our temperature is going to be 305 Kelvin. And then the R value we're going to use for this is going to be the 8.31 because the units are in kilopascal. Okay, so the units for pressure. So the units for pressure is what determines what you use for R. Okay, so if it's kilopascal, it's 8.31. So now we have to figure out the mass of krypton. Okay, so if you think back to stoichiometry, we can do a lot with stoichiometry. We know that we can find the amount of moles using a mass and vice versa, right? So if we're trying to figure out the mass of the krypton, we're first going to have to calculate the amount of moles of krypton that are needed to fill this balloon in this situation. So that being said, we're going to find N. We know that our formula is PV equals nRT. Okay, we have pressure, we have volume, we have R, and we have temperature. We're solving for N, okay? So we're just going to get started. So our pressure is going to be 104.8 times the volume of 11.0. Is that equal to N? Okay, and we'll deal with the mass after we solve for N. We're going to have R, which is 8.31, times the temperature of 305. Okay, so we're going to go ahead and just calculate this. We're going to end up with 104.8 times 11 divided by 8.31 times 305. Okay, so this is telling us that N is going to equal 0.455 moles. Okay, so that's 0.455 moles of krypton. Okay, and it wants the mass. Okay, so we're almost done. Now you just have to convert the moles of krypton into the mass of krypton. So if we do this just like any other stoic problem, we're going to have 0.455 moles of krypton. Okay, we know moles of krypton is going to have to come down. Okay, and then what goes on top, it's what the molar mass is. So if we're going to look on our periodic table, handy dandy, we're going to find krypton and see that its mass is 83.79 grams. Okay, and now you just solve for that. So you're just taking what you literally just had and multiplying it by the mass. Okay, so you're saying that you're going to have 38.11 grams of krypton in this situation. Okay, so that's your entire answer. So these are really just algebra. If you're feeling okay about algebra, everything will fall into place with these. There's kind of a systematic way to approach them. So with these problems, just keep in mind that you can be solving for any of these 5 variables. And the one thing about moles that's special is that you can use that in a stoichiometry problem. So this could be part of a larger question. Just kind of be aware of that and be looking out for that. So if you're reading something and you're like, I don't know what this is going for, it's probably wanting you to calculate N and then do something with that. So if it's not clear, it's probably that. So this would be how you do this example. We're going to go ahead and do another example here. Okay, erase all this. And each of these examples are a little bit different. So if you're thinking like, I got this is good, I can stop watching, that's fine. But all the problems are solved a little bit differently usually. So I'm just going to go through the other 3. And if you want to follow along, go ahead. So example 2 is saying that you have a sample of oxygen, occupies a volume of 1.5 liters. under a pressure of 109.2 kilopascal at a temperature of 26 degrees Celsius. Determine the mass of oxygen in the sample. So this is going to be similar to the last one. So we're going to start out here pulling out the variables that we know. The volume is going to be 1.5 liters. The pressure is 109.2 kilopascals. Temperature is 26 degrees Celsius, so 26 plus 273 is going to give you 299 Kelvin. Okay, and when you write, I don't know if this is something I've talked about before or not, but when you write Kelvin, it's not like degrees Kelvin, like you would with Fahrenheit and Celsius. It's just K. So just so you know. So since our pressure is in kilopascal, we know that our R constant will be 8.31. And we know, obviously, that we have PV equals nRT. Okay. So what we're looking for is the mass, which means we're going to have to find the moles. Okay, that's common with this. So if it's asking for mass, and this is the kind of information you have, you're going to have to find the moles and then convert it into mass. So with these, you're just going to plug it in and solve. So you have 109.2 for our volume, our pressure. Volume is 1.5. We're going to set that equal to N times 8.31, because that's our R constant. And the temperature was 299 Kelvin. So the number of moles here, we're just going to plug all this in. It's going to be 109.2 times 1.5 divided by 8.31 times 299. Okay, it's going to give you 0.066 moles of oxygen. Okay, so now we have to find the mass, and that's just a simple stoichiometry problem at that point. Okay, so if I'm just going to write it off this, I'll do it in different color. So if I start with this many moles of oxygen, I'm going to have 1 mole of oxygen on bottom. We know that oxygen is 15.99 grams. Okay, so at that point, you're just multiplying it. So we're going to take what we had, we're going to multiply that by the mass of oxygen to get 1.05 grams of oxygen. Okay, so just keep in mind, this doesn't tell us whether it's O or O2. I'm just going with O because we don't know either way. It could be O2. So most problems will specify O2 or not. So that's what we've got here, right? So that was kind of the same type of problem. Now the next problem will be different. So let me erase all this and we will move on to our next type of problem. Okay. All right. So number 3, we have an unknown gas with a mass of 0.0662 grams, occupies a volume of 56 milliliters at a temperature of 30.4 degrees Celsius under a pressure of 1.09 atmospheres. Determine the name of the gas. So let's pull out what we know. Okay, we are trying to find the name of the gas. So if we think about this logically, how can you identify something, an element, by a number? Probably not by moles because we don't have that on the periodic table. But what we do have on the periodic table are all of their masses, right? So if we're trying to determine an unknown, if it's just a single element, that's pretty easy, right? So we're just going to figure out the mass again, and then identify that on your periodic table and match it up, okay? So here we have an unknown gas. Let's see. It has a mass here that's occupying a volume. Let's see. So the mass, and I guess I should clarify, the mass that's given in the problem is the mass of the sample. It's not the molar mass. Okay, so we need to find the molar mass, which we're going to get from finding moles first. So let's see here. We've got, we'll put this in. volume is 56 milliliters. Okay, so that's going to be 0.056 liters, has to be in liters. Pressure is 1.09 atmospheres. Because it's in atmospheres, we're going to use, oh, I just lost it. Yep, right here. We're going to use the 0.08205 for R. Okay, so when it's in atmospheres, you're using this smaller number. And then, let me see here, what else do we have? Temperature is 30.04, so, or 30.4 plus 273 is going to be 303.4 Kelvin. And then we have N. Okay, so N is where this gets a little weird because we're trying to find the name of the gas. So we know that we need to find the mass of the gas, right? So for this, we know that the mass that we're working with is the 0.0662 grams of the unknown substance. We need to find its molar mass, right? So if we're going to do that, let's see. We know that if we were doing stoichiometry, grams would have to come down here because grams is here. And that's always going to be equal to 1 mole of whatever this substance is. So we don't know what this is. This is what we're solving for, okay? So when we want to put this into the equation, I'm going to say that N is equal to 0.0662 over X. All right? So one of your questions on your assignment is very similar to this. So we're trying to find the name of the gas. We need to know its molar mass, okay? And you can do that just like we did before with these simple stoich problems. You have the sample size. We would have put in the molar mass here equal to 1 mole to find moles, but we don't know molar mass. So we're going to simplify this equation. This is going to be what we put in for the variable of N, and then we're going to solve for that X. Okay, the X is going to be the molar mass. So we're going to plug all this in. We know it's PV equals nRT, so we're going to have 1.09 times 0.056 liters equals to N, which is going to be this for now, 0.0662 over X times R, 0.08205 times our temperature of 303.4. Okay, so now we have to break it down and solve for X. So if I want to isolate this portion, we're going to solve it basically the same way as we've done the others. So 1.09 times 0.056 divided by 0.08205 times 303.4. Okay, so that's going to give you 0.0025 set equal to this. Okay, and then now this is just algebra. You just have to solve for X. So we're going to, you can cross multiply and divide. So that's what we're going to do. So you're going to end up with 0.0662, let's see, divided by the 0.0025. Okay, so that's going to tell you that X is equal to 26.48 grams. That's its molar mass. So that means we can look on our periodic table and identify it. It's going to be aluminum. Okay, I don't know if you can even see that, but aluminum has a mass of 26.98. Okay, so 26.48, 26.98, that's within the range. It's not going to be closer to any other element. It might be just slightly off there because we rounded somewhere. Okay, so this is going to tell us that aluminum is our answer. Okay, and feel free to go through and screenshot these if you want to keep them as notes. So this example is the second to last one. It was done the same way as the first two, pretty much, with just a small variation with in. So like I said before, in is where it gets a little complicated sometimes, but you can do it. I know you can. And if you can't, let me know, please, and we'll set up a Zoom or something. Okay, so keep in mind also the test is coming up. So if you are super lost on any of this, please let me know. I would much rather set up a Zoom meeting or write a detailed email or make another video or have you come in or something than have you like panicking at the last second. So please let me know if you do need help. Let's erase all this good stuff. All right, so this will be our last example, is example number 4. Okay. I should move my mouse. Alrighty, so let's get all these down. I got this kind of messy. And let me get my pen. Alright, so now this one's just slightly different, and I'm sure you can guess that we're going to have to use some stoichiometry here since there's a formula involved, and we're going to have to use a mole ratio. Okay, so here we have the balanced equation. That part was given in this question. The balanced equation may not be given on the test, so just beware that like that skill is not going away. So determine the volume of water produced when 7 grams of methane is reacted with excess oxygen with a temperature of 120 degrees Celsius and a pressure of 1.2 atmospheres. Okay, so we are going to get this ready. All right, so let's see, what are we finding here? We're finding the volume, which means we have to have the pressure. So if we're finding volume, we have to have the pressure, the temperature, the R, which we could have, and we have to have the moles. So based off of this, we have to find the moles first. We have to find in first before we can get started. So for this one, we're going to start out finding in. Let's see here. So if it starts us with 7 grams of CH4, we're trying to figure out the volume of water produced. So we need to convert this into water, moles of water. So if we have 7 grams of CH4, we know that grams of CH4 has to go on the bottom. So we're just going to add that up and get its molecular mass, which is 16.04 grams. Okay. We know that that's equal to 1 mole of methane. And then now you're going to use your mole ratio up here to convert it into water. So here we know that moles of methane has to be on bottom. So if you look at your mole ratio, there's 1 mole of methane for every 2 moles of water. So we're going to have 1 mole of methane down here because 1 mole of methane has to come down, set to 2 moles of water. Okay? So then we're going to solve that to find in. All right, so we're going to have our 7.0 times 1 times 2 all divided by 16.04 times 1. Okay, so that gives us an in value of 0.873 moles. Okay, so it's a lot of work to find one variable, but that's how you do it. Okay, so now we know in. We're trying to find volume. So what else do we have here? Okay, so we have the temperature. Okay, it's in Celsius, so we're gonna have 120 plus 273 gives you 393 Kelvin. And then we're gonna have pressure is gonna be 1.2 atmospheres. And then we need the R value. So since pressure is in atmospheres, we're gonna go ahead and use the, the 0.08205. Okay. Now we can solve. So we know that that's in temperature, pressure, R, and we need the volume. So I'm going to switch my colors one more time. Okay, so we know we have PV equals nRT. Pressure is going to be 1.2 times volume, which we don't know, is equal to N, which we calculated is 0.873 times R, which is this value, 0.08205, times your temperature of 393. Okay, so now we need to isolate V. So we are going to do a little math. All right, so we're going to end up with 0.873 times 0.08205. 0.08205, missed that, okay, times 393. That would all be divided by 1.2. All right, so you should end up with V being equal to 23.46 liters. Okay, and that's it. So make sure you are always showing your work. You have to show your work, okay? Always be labeling throughout. Please don't just write numbers in your dimensional analysis because 9 times out of 10, you're going to lose track. And then if you look back on it, you're not going to have any idea what you're looking at. So this can be useful for future questions if you have it labeled, because if you get the same formula to analyze, then you can just refer back to this and you have it all, that part done already. So if you don't label it, you don't know what you have, and then you're probably doing more work in the long run. So make sure you're always labeling things, including all of your variables and especially your answer, okay? And that's it for today. So that's all we're doing is the ideal gas law. You do have an assignment on Canvas. It's 7 questions, I think. They're all like these, so I know it'll take a little bit of time, but the answers are at the very bottom of the last page if you want to double check as you go through. Make sure you have units and make sure you're showing your work. And if you do have any questions, please let me know. So hope that works out for you. Let me know if you have questions and I will talk to you guys next time.